Now we're going to see more undecidable problems. We begin with Rice's theorem, which tells us that almost every question we can ask about the recursively enumerable languages is undecidable. And we then introduce a problem called post-correspondence problem, which we also show is undecidable. Post problem does not appear to have anything to do with Turing machines, so the fact that we can show it as undecidable is a valuable step on our road toward showing real problems undecidable. However, post problem is still just a game, but we can use post problem to show some real problems, for example, questions about grammars, to be undecidable. We'll first see Rice's theorem. That theorem involves what are called properties of languages. Formally, a property of languages is any set of languages, the languages that we say have this property. For example, the property of being infinite is the set of infinite languages. The property of being empty is the set containing only the empty language. While properties like being infinite apply to any language, even not recursively enumerable ones, we need to represent languages, and the Turing machine is the most powerful tool we have for representing languages. So we'll talk about properties of recursively enumerable languages only. So we'll consider a property to be a problem about Turing machines. Given a code for a Turing machine, does it define a language with that property? So for any property P, we can define a language L sub P, the set of binary strings that represent a Turing machine whose language has the property P. So for example, L sub infinite is the set of codes of Turing machines that define an infinite language. There are two properties we call trivial for reasons that will be obvious. For these two properties P, L sub P is decidable. One of these trivial properties is the always false property that contains no recursively enumerable languages. We can think of this property as is not a recursively enumerable language. This property is actually true of some languages, but those are outside the recursively enumerable class, obviously, and we're talking about properties only as applied to the recursively enumerable languages. How do we decide this property? Given an input W, we ignore it and say no. Notice that even if W represents an invalid Turing machine code, we have agreed to take all those strings as representing a Turing machine that accepts the empty language. But the empty language is a recursively enumerable language, so we are correct in saying that W's Turing machine does not have this property. The second trivial property is the always true property. We could express the property as is a recursively enumerable language. The algorithm for this property is to ignore the input and say yes. And Rice's theorem says, for every property P except the two trivial ones, L sub P is undecidable. An important part of the proof of Rice's theorem, which we'll be working on for a while, is the idea of a reduction. There are actually several different notions of reduction. We'll come back to that point later. But the simplest one, and the one we need for Rice's theorem, is an algorithm that takes an input string W for one language, or problem L, and converts it to another string X that is an input to another language or problem L prime, with the property that X is in L prime if and only if W is in L. The value of having such a reduction is that it tells us L is no harder than L prime, at least as far as decidability is concerned. If I know L prime is recursively enumerable, then I also have a Turing machine program for L. If I know L prime is recursive, then I also have an algorithm for L. In either case, the solution for L is to take the input W, convert it to X, see what the Turing machine for L prime does, and take its output to be that answer for W. The thing that turns a string W into X is called a transducer. So far we've only talked about a Turing machine whose only output is the yes or no that is implied by accepting or halting without accepting, respectively. But we can get other kinds of output from a multi-tape Turing machine if we designate one of its tapes to be the output tape and regard what is written there when the machine halts as its output. We could, for example, imagine such a transducer that takes W on its input tape and writes X on its output tape and then halts. So if we reduce language L to L prime using such a transducer, and L prime is decidable, that is, there is an algorithm to test membership in L prime, then there is also an algorithm for L. That is, we start by applying the transducer to input W and producing output X. We apply the algorithm for L prime to input X and decide whether or not X is an L prime. Either way, the algorithm renders a decision, either yes or no. And these two steps form an algorithm for L. The whole thing takes input W and tells us whether or not W is an L. We sometimes see a reduction used to discover an algorithm for L, but the more important use of the idea is in the contrapositive. If we already know that there is no algorithm for L, then there cannot be any algorithm for L prime. That's how we're going to use reductions. We'll take one problem that we may not be interested in, but that we know is undecidable, and reduce it to another problem that we are really interested in, but whose status we don't yet know, and then we will conclude that the second problem is also undecidable. Moreover, when we get to intractability, or the theory of NP completeness, we'll be using reductions that are fast to argue that a problem like L prime can't be solved faster than the problem L. There are more powerful forms of reduction that let us reach the same conclusion. That is, if there is an algorithm for L prime, then there is an algorithm for L. We actually saw one example of a more complex reduction where we started by assuming that there was an algorithm for L sub u, the universal language, and showed how we could then construct an algorithm for LD which we know does not exist. However, the hypothetical algorithm we constructed for L sub D involved more than just turning one string into another. We first had to check whether the input W was a well-formed code for a Turing machine, and if not, we answered the question directly. Moreover, after doing a transduction where we turned input W into W111W, we had to complement the answer that we got from the hypothetical algorithm for L sub U. That is, we turned a yes answer into no, and vice versa. In the simple version of reduction, we are not allowed to modify answers in this way. We have to take whatever answer we get. We'll revisit this issue of more general kinds of reductions when we talk about NP completeness. There, the simple reduction is called a Karp reduction, and more general kinds of reductions are called Cook reductions. Steve Cook and Richard Karp, by the way, were the people who made the earliest contributions to NP completeness theory. We're now ready to prove Rice's theorem. The idea is that we can reduce L sub u to L sub p for any non-trivial property p. Then, since we know L sub u is undecidable, it follows that L sub p is undecidable. Here's how we reduce LU to LP. The input to LU is a Turing machine M and an input W for M. The output will be the code for a Turing machine M prime. That is at least the right form, since LP is a set of Turing machine codes, those for which the language of the machine has property P. Of course, for the transduction from M and W to M prime to work, we must arrange that M prime has property P if and only if M accepts W. That is, M prime is an L sub P if and only if M and W is an L sub U. We'll design M prime to be a two-tape machine. On the first tape, M prime simulates another particular Turing machine which we'll call M sub L on its own input, say X. On the second tape, M prime simulates M on W. It is important to understand that M prime has only its own input X, which the transducer does not deal with, or C. The transducer knows about M sub L. It is built into the design of the transducer. The transducer gets to see the code for M and the string W, that is on its own input. Thus, the transducer can build both the moves of M and the input W into the transition function of the machine M prime, that is its own output. None of M sub L, or W is input to M prime. We're going to assume that the empty language does not have property P. If that is not the case, then consider the complement of P, say Q. Surely the empty language then has property Q, but if we could prove that Q were undecidable, then P also must be undecidable. That is, if LP were a recursive language, then so would be LQ, since the class of recursive languages is closed under complementation. So let L be any language with property P. We know L exists because P is not trivial. Also, let M sub L be the Turing machine that accepts L. Here's how M prime behaves. To begin, M prime writes W on its second tape. It can do that because the transducer seeing W generates a sequence of states that write W one bit at a time. M prime, from its start state, enters each of these states in turn. Then M prime moves the tape head for tape 2 to the left end, goes to the start state of M and simulates W on input W. Again, M prime can do that because the transducer sees both M and W and makes the transition function of M part of the transition function of M prime. Suppose during the simulation of M on W, M enters an accepting state. Then M prime goes to the start state of M sub L and simulates M sub L on the input X to M prime, which has been just sitting there on tape 1 being ignored so far. Where does M prime get the transition function for M sub L? M sub L is a particular Turing machine, one that accepts a language L with property P. Thus, the transducer itself can be designed so that it writes the transitions of M sub L out as part of the transition function of M prime. If M sub L accepts the input X, then M prime enters an accepting state. If M sub L never accepts X, neither does M prime. Thus, if M prime ever gets to the stage where it simulates M sub L, then M prime accepts the same language as M sub L does, that is L. But if M does not accept W, then M prime never gets to the stages where it simulates M sub L, and therefore M prime accepts nothing. Here's a picture to help us remember what M prime does. It first simulates M on input W. So far, M prime's own input, X, is ignored. But if M accepts W, then M prime simulates M sub L on its own input X. And M prime accepts X if and only if X is in L. So to summarize what we know about M prime, first, suppose M accepts W. Then M prime simulates M sub L on X and accepts X if and only if X is in L. That is, if M accepts W, then the language of M prime is L. We know L has property P, so M prime is in LP. Now look at the opposite case where M does not accept W. Then M prime never even starts the simulation of ML, and therefore M prime cannot accept its input X. That is, in this case, the language of M prime is the empty language. We know the empty language does not have property P. Thus, if M does not accept W, M prime is not in the language LP. We conclude that the algorithm we described for converting M and W to M prime is a reduction of L sub U to LP, and therefore that LP is undecidable. That is Rice's theorem. This is a picture that reviews the argument for why the existence of the reduction from LU to LP proves LP is undecidable. We have a real reduction algorithm. I hope you are convinced that you could program this algorithm if you were paid enough. We then contradict the hypothesis that LP has an algorithm by supposing that algorithm existed. Then you could put together the reduction plus the hypothetical algorithm to build an algorithm for LU. Since we already proved that there is no such thing, we have to look at what of this story hasn't been proved. The finger points at the hypothetical algorithm for LP. Since we didn't prove it exists, we just assumed it did. Thus, the assumption must be responsible for the false conclusion, and we can conclude instead that there is no algorithm for property P. Thanks to Rice's theorem, we suddenly have an infinite collection of undecidable problems about the languages defined by Turing machines. Here is just a tiny sample of the questions that are undecidable about Turing machines M. Is M's language regular? Or is it context-free? Does this language include at least one string that is a palindrome, that is, a string that is the same as its reversal? Is the language empty? That is, does M accept any string at all? Does the language contain at least 1,000 strings? But Rice's theorem also applies to programs, since you can write a program to simulate a Turing machine. That tells us any non-trivial question about what a program does will also be undecidable. I want to emphasize about what a program does. There are lots of questions about what a program looks like that are decidable. For example, I can tell whether a program uses more than 20 variable names, but that's not a question about what the program does. An example of a question about what a program does is, does the program eventually halt on any input? That is undecidable. Or, does the program correctly sort its input? That's undecidable. Or, does this line of code ever get executed? That's undecidable. We're now going to take up post-correspondence problem, affectionately known as PCP. PCP is the first example of a problem that is undecidable yet doesn't involve Turing machines or programs, which are really the same thing. As we said, PCP is not really important by itself since it's just a made-up problem, but it leads us to proofs that many other problems are undecidable. These problems are unrelated to Turing machines but are related to matters like context-free languages that were not developed for the purpose of exposing undecidable problems. That is, we studied grammars for their use in matters like describing the structure of programming languages. We had no intent to describe problems that turned out to be undecidable. It just turned out that there were undecidable problems lurking in the theory of context-free grammars. An instance of PCP is a list of corresponding strings. That is, a list of pairs of strings over some particular alphabet sigma. The instance has some number of pairs, say n. The first pair is w1x1, the second is w2x2, and so on. None of these strings can be the empty string. The property of the list that makes the answer to this instance of PCP be yes is that when we take the first component from each pair on the list, that is, wi1 is actually the first component of the pair that we indexed as I sub 1. I can't draw on the slide two levels of subscripts. Then the second wi2 is that w from this list that has in the I that is from the I-tooth pair on that list, and so on. Then we get the same string if we take the w's from the pairs as if we took the second components or the x's from the pairs. Okay. Such a list of integers is called a solution to the instance of PCP. Here's a simple example instance of PCP. The alphabet will be 0 and 1. And there are two pairs. The first pair is 0 and 0, 1. The second pair is 1, 0, 0 and 0, 0, 1. Okay. Every time a list of integers has 1, it refers to this pair, and every time it has a 2, it refers to that pair. Okay. In this case, it turns out there is no solution to this instance of PCP. The analysis of this simple instance is not so easy. The easy part is that no solution can start with the second pair. Why? The reason is that if we choose 2 as the first integer in the so-called solution list, then the first string made from the w's that are first components will begin with this 1. But the second string, the one made from the corresponding x's that are the second components, begins with this 0. I don't care how you continue, a string that begins with 1 can never equal a string that begins with 0. However, it is possible that the solution list begins with index 1 because for pair 1 the two strings are not inconsistent, that is, one is a prefix of the other. So let's see if we can build a solution starting with the first pair. Since the two strings are not equal, we have to add another pair. We can't choose pair 1 because the first string would then begin 0, 0, and the second string would begin 0, 1. That could never lead to a solution. So the second index in the solution must be 2. Now both strings begin with 0, 1, 0, 0, and the second string has an additional 1. We're back where we were at the previous choice. We can't pick 1 as the third index, but we can pick 2, and we get a match up to a point, with the second string again having an additional 1. If you think about it, we can never make the two strings be the same because to do so we'd eventually have to use a pair whose second string was shorter than the first. But there is no such pair in this instance. We conclude that this instance has answer no. On the other hand, let's change the instance a little by adding a third pair, 1, 1, 0, and 1, 0. Now the list of indexes 1, 3 is a solution. From the first strings of the pairs, we get 0 followed by 1, 1, 0, which is 0, 1, 1, 0. That is, 0, 1, 1, 0 is a 0 followed by a 1, 1, 0. From the corresponding second strings, we get 0, 1, that's this, followed by 1, 0, that's that, and that also is 0, 1, 1, 0. In fact, there is an infinity of solutions for this instance. Any string of indexes in the language of regular expression 1 to star 3. That is, after the 1, we can use pair 2 any number of times, including 0, obviously, and finally use the pair 3. So here's the plan for proving PCP is undecidable. We're going to start by introducing a modified version of the problem called MPCP, or the modified post-correspondence problem. The modification is that a solution to MPCP must begin with the first pair, but otherwise the modified and original PCP problems are the same. We'll show how to reduce L sub u, the universal Turing machine language, to MPCP, and then we'll show how to reduce MPCP to P sub p. In fact, this part is easier, so we'll do it first. Just to get the distinction between PCP and MPCP clearer, observe that if we treat the list of 3 pairs from our previous example of PCP as an instance of MPCP, then the answer is yes. The reason is that there is a sequence of indexes beginning with 1, say 1, 3, that produces equal strings from the first and second components of the pairs. But we can reorder the pairs, say by putting 1, 1, 0 and 1, 0 first. As an instance of PCP, order of pairs doesn't matter. There is still a solution. But as an instance of MPCP, there is now no solution. Any solution would have to begin with index 1, but then the first of the 2 strings would begin 1, 1, 0, and the second would begin 1, 0. So no matter how we extend these strings, they disagree in the second positions, and so they are not equal. Before we can talk about reductions, we need to express PCP and MPCP as languages. The instances of these problems can have any alphabet. So it is not immediately obvious how to express the set of all PCP instances that have a solution. Again, the problem is that there is no finite alphabet for this set, and languages just need a finite alphabet. So we need to code symbols in a finite alphabet. We'll represent the ith symbol of an alphabet by the symbol A followed by I in binary. Thus we only need 3 symbols to represent any number of symbols. The order of symbols of the alphabet is not important. For example, if we have an instance over alphabet A through Z, we could represent A by A1, B by A10, and so on. But we could also represent Z by A1 and Y by A10 and so on. It should be clear that the particular symbols used for the alphabet of a PCP instance does not affect the outcome. And the only other symbols we need to represent instances is the comma and left and right parentheses. Thus the alphabet for the language of PCP instances will have an alphabet of 6 symbols, the A, 0, 1, comma, left paren, and right paren. Now that we have a finite alphabet for coding instances, we can define 2 languages. L sub PCP, the language of coded instances of PCP that have a solution, and L sub MPCP is the same for the modified problem. Now we can do the reduction of MPCP to PCP. We'll describe the transformation only, but you should be able to visualize the process being performed by a Turing machine transducer. Our input is an instance of MPCP. The output instance of PCP will use the same alphabet as the input instance, plus 2 new symbols, the star and the $sign. Of course, all symbols, the new ones and the symbols in the input instance of MPCP will be coded using A, zeros, and ones as we just described. For each pair WX in the input instance, there is a pair in the output instance based on W and X. For every first string W of the pair, we add star after every symbol. So for example, 0, 1 becomes 0 star 1 star. And for X, the second string of the pair, we instead add a star before every character. So for example, 1, 1 becomes star 1 star 1. The output instance also has a new pair unrelated to any input pair. This pair is $sign paired with star $sign. And the output also has a second pair based on the first input pair. This pair has stars placed after the symbols of the first string and before the symbols of the second string, just like in rules 1 and 2 on the slide. But the first string also has a star at the beginning. So for example, the pair 0, 1 paired with 0 would become star 0 star 1 star paired with star 0. Here's an example. On the left is the instance of MPCP that is input to the transducer. On the right are those pairs with the added stars. Notice that for each pair, the stars come after the symbols on the first string and before the symbols on the second string. And we always add this pair, which will serve to make the strings of the PCP instance match when there is a solution to the MPCP instance. Its job is to add the missing star to the second string. And this pair also comes from the first pair. It is just like the first pair of the PCP instance, except for the star at the beginning of the first string. Notice that this is the only pair in the entire PCP instance where both strings start with the same symbol. For example, this pair has 0 as the first symbol of the first string and star as the first symbol of the second string. Okay. All these pairs have second strings that begin with star and a first string that begins with 0 or 1. Suppose the MPCP instance has a solution, a sequence of indexes that yield string W when we use the first strings in the pairs and the same string W when we use the second strings. Then we can get a solution to the constructed PCP instance. In this case, the solution string will be W padded with stars before each symbol of W and also at the end followed by the $sign. For example, if W is 101, then the PCP instance's solution is star 1 star 0 star 1 star $sign. To get the PCP solution, we use the same sequence of indexes as in the solution to the MPCP instance with two exceptions. First, we use the index of the special pair as the first index. Recall this pair was constructed from the first pair of the MPCP instance with the extra star. And we also add to the solution of the PCP instance the index of the ender pair star, dollar, and dollar to the end of the list of indexes. Thus, a solution to the input MPCP instance means that the output PCP instance also has a solution. But the other direction also holds. If the PCP instance has a solution, we can modify it to get a solution for the input MPCP instance. The first index in the PCP solution must be the special pair because that's the only pair of the PCP instance where both strings start with the same symbol. To change this index to 1, the index of the first pair of the MPCP index. Leave all the other indexes unchanged, but remove from the PCP solution the last index, which must be the index of the ender pair. Why? That's the only pair where both strings end with the same symbol. Thus we've shown that the answer to the questions, does the input MPCP instance have a solution, and does the output PCP instance have a solution, are the same. That means we have a valid reduction from MPCP to PCP. If we can prove MPCP is undecidable, which we'll do next, then we have a proof that PCP is also undecidable. So our next task is to show how to reduce L sub U to MPCP. Given an instance m and w of L sub u, we'll convert this to an instance of MPCP whose only possible solutions yield strings that represent the sequence of IDs that m enters when its input is w. More precisely, suppose this sequence is a sequence of IDs that m enters, starting with the initial ID with input w. Then any solution to the constructed MPCP instance will yield a pair of strings that begin with the sequence of IDs separated by pound signs. However, until m enters an accepting state, when we look at the two strings of the partial solution, one formed from the first strings of the indexed pairs and the second from the second strings of the indexed pairs, the second string will always be a full ID ahead of the first string. Only if m accepts will we be able to choose pairs that make the first string grow faster than the second and eventually make the two strings become identical. We're going to assume, as we can, that the Turing machine m from the input to L sub u has a semi-infinite tape and never moves left from the initial head position. That is, given the actual binary string representing m, we can modify the represented machine to mark its left end of tape, as we did when we described the construction of a Turing machine with a semi-infinite tape from one that had a two-infinite tape. Then we can perform the reduction on the new Turing machine that we know does the same as m rather than on m itself. However, in what follows, we will continue to refer to the input machine as m. The MPCP instance we construct will have an alphabet that consists of all the states and tape symbols of m, or rather the modified m, plus the special marker pound sign. We assume that the symbols used for states and tape symbols are disjoint, so we can tell one from another in the ID. Here's the beginning of the construction of the MPCP instance from m and w. The first pair has a first string that is just a pound sign, but a second string that is the entire first ID with input w, surrounded by pound signs. Note that the transducer gets the CW on its input so it can generate this pair. We'll add the pair pound sign, pound sign. It lets us add markers to the end of one ID in the first string at the same time we add it to the following ID in the second string. Add pair XX for every tape symbol X. This pair lets us add an X to the ID we're forming in the first string at the same time we add an X to the next ID, which is being formed on the second string. Of course, in order to make sure that the strings match, it must be the case that an X appears as the first unmatched symbol of the second string. Recall, the second string is one ID ahead, so these pairs, in effect, let us copy the tape of one ID to the next ID, but prevents us from making changes that are not justified by a move of m. Here's a picture of copying IDs. Suppose we have just reached a point in the sequence of indexes when the second string has a complete ID more than the first string, but otherwise the strings match. We can add to the solution we're constructing the pair AA. That has the effect of putting the first symbol of the new ID at the end of the first string and also extending the second string by the same symbol. That's what we want, since there's no way this A could change in the next ID. We can also then add the index of the pair BB to the solution, extending the new ID one symbol further. This might or might not be the right thing to do. The problem is that if the move of m in state Q with symbol C is to move left, then the second symbol of the new ID is the new state, and B will be the third symbol. But just because we can choose the pair BB doesn't mean we have to. If m is going to move left, there will be another choice of next index that simulates the move correctly, and the sequence where BB is chosen instead will fail to yield a solution to the MPCP instance we're constructing. Now we need to add the pairs that reflect the moves of m. For every state Q in tape symbol X, if the move of m is to the right, say PYR, we have a pair in which Q to the left of X, that's this, can be replaced by a P to the right of Y. That correctly reflects the change in ID that occurs at the rightward move. And if the move is to the left, then we have a family of pairs, one for each symbol Z that could appear to the left of the state. Note that we arranged that M can never move left from its initial position, so there is no possibility that the state is at the left end of the ID if M moves left. So if the leftward move has state Q and symbol X replaced by state P and symbol Y, then for every Z there is a pair that puts P to the left of the Z and replaces the X by the Y. One other possibility is that in the current ID, the state is at the right end of the ID, scanning a blank we've never visited before. If so, the state will actually be to the left of the pound sign. Okay, and the pairs are almost the same, but when constructing the second string, we should imagine an extra blank in front of the pound sign. The blank is replaced by the new symbol Y, of course. Following our previous example, suppose that in state Q, scanning C, M does indeed move right, going to state P and writing E in place of C. Had M moved left in that situation, the sequence of pair choices would be dead in the water, unable to continue. However, in that case, we could have chosen not to use the pair BB, but instead use a pair that incorporated the left move and handled the B properly. In this case, we have a pair with QC as the first string, so we can match the string on the bottom. It also extends the bottom string with EP, reflecting a move of M. Once the move has been handled, we can just match symbol against symbol. Here the pair DD is used. And once we are at the end of the ID, we use the pair of pound signs to separate the IDs, and we're now ready to continue the sequence of pair choices to copy the new ID, which is ABEPD, and make it changed by another move. But we need some more pairs in the MPCP instance so that in case M accepts, we can find a solution. Note that if M never accepts, then only the rules given so far can ever be used, and these can never lead to a solution because the second string is always one ID longer than the first. However, if M enters a final state F, then it is possible for the F to, we'll say, eat the neighboring symbols of an ID. We no longer have real IDs of M, but it doesn't matter. We've simulated M enough to know that M accepts W, and our only concern then is to make sure that there's a solution to the MPC instance based on M and W. Thus, we add to the instance of MPCP pairs XFYF, FYF, and XFF for all tape symbols X and Y. Using these pairs, together with pairs of the form XX to copy parts of IDs as we have done, we eventually get to an ID that is only the state of F. Of course, that isn't an actual ID of M, but it doesn't matter anymore. And one more pair, F pound pound, paired with the pound sign, will end the two strings being formed, making them the same and yielding a solution to the MPCP instance. So here's an example where M has entered the final state F, and a sequence of choices, either copying a symbol or allowing F to eat the adjacent symbol or symbols, eventually leads to identical strings. So here's what it looks like. Well, we'll just have to copy that A, but now the F can in effect eat the B and C adjacent to it. We have to copy the D, we have to copy the E, we have to copy the pound sign. Now the F can eat the A and the D, but we have to copy the E, have to copy the pound sign. Now F doesn't have anything that it can eat to its left, but it still will eat the E. And finally, copy the pound sign, and now F pound pound paired with pound makes everything evened up, and we have our solution. Now we know that PCP is undecidable because we successfully reduced L sub U to its own language, M sub PCP. And we're going to reduce PCP to the problem, is a context-free grammar ambiguous? Then, for the first time, we'll have an undecidable problem that arose naturally. That is, not because we were looking for undecidable problems. Before we can talk about any problem involving grammars, we need to find a code for grammars using a finite alphabet, just as we did for PCP. So to start the encoding of grammars, let's represent the ith terminal by symbol A followed by I in binary. That may look like with us forgetting what the actual terminal symbols are, but since we're interested in ambiguity, we can rename the terminals any way we like as long as we don't name two terminals the same, and the ambiguity or unambiguity of the grammar will not change. Then we'll represent the ith variable by capital A followed by I in binary. We will assume that A1 is always the start symbol. The right arrow between the head and body of a production will be represented by itself. Likewise, the comma separating productions and the symbol epsilon will represent themselves. For example, this grammar is represented by this string right here. The bar connecting alternative bodies for S has been expanded so that there are two separate productions. This represents S goes to 0S1, and this much represents S goes to capital A. Finally, this represents capital A goes to little c. Suppose we have a PCP instance with k pairs, and let the ith pair be wi xi. We need k index symbols to represent the numbers of the pairs, and we'll use A1 through AK, which we may choose to be symbols that do not appear in the PCP instance itself. Notice that we're going to talk about reducing an uncoded instance of PCP, so it can have any alphabet, to an uncoded grammar, which also can have any symbols. However, the process we describe really takes place with all the symbols coded in the manners we have described. It is easier to follow the construction in the uncoded form, so that's what we'll do. The list language for the first half of each pair, the strings W1 through WK, has a context-free grammar with productions A goes to WI, capital A, little ai. It also has the same sort of production, that, but with A omitted from the body. The latter kind of productions, these, are used to end the derivations. All the strings in this language are some sequence of the WIs with repetitions allowed and in any order, with the corresponding index symbols following, but in reverse. For example, here's a derivation. Okay, A could derive in one step, let's say W1, A, little a1. And then in one more step, we could use, let's say, the terminal production for W2. So we get W1, W2, and then A2, A1. Notice that the sequence of A's is the reverse of the sequence of W's. And we can do the same thing with the second string from each pair. We'll use variable B and xi's in place of wi's, but the idea is the same. The language of strings generated from A and B each consist of a concatenation of strings, either from the wi's if it's A or the xi's if it's B, and these are the first or second components of the pairs. They're followed by the reverse of the sequence of indexes of the pairs from which these strings came. Here's an example of a PCP instance over alphabet AB. We'll use 1, 2, and 3 as the index symbols. So the grammar with start symbol A is this. For example, the second pair, whose first string is BAA, gives rise to these two productions. Here's BAA with the variable A in the middle, and then 2, which is the index. And then there's another production that's the same but without the capital A. And here's the grammar for the second strings in the pairs with start symbol B. As an example, if we choose the three pairs in order 1, 2, 3, then there's a derivation from A that looks like this. So A, use the first choice, that's this production. Then we'll use the second choice, which is this production, and that gives us A, B, A, capital A, the 2, and the 1. And then we'll use the third pair, but we want to end it, so we'll use that production, and that gives us A, B, A, B, A, sorry, B, B, A. That's that. And then 3, 2, 1. We're now ready to show how to reduce PCP to the ambiguity problem. Given the PCP instance, construct the two list languages with variable A for the first strings of the pairs and B for the second strings of the pairs. Then add the productions S goes to A and S goes to B. Of course, S is the start symbol of the grammar. Okay. We'll show the resulting grammar is ambiguous if and only if there's a solution to this instance of PCP. But first, let's look at an example that should actually expose how the proof in general works. Okay. Here's the grammar constructed from the PCP instance that we saw earlier. It is the sets of A productions and B productions we saw plus the two productions for S. Okay, notice there is a solution 1, 3. That is, the first pair was A, and the third pair was BBA with BA. When we take the first strings of each pair, we get ABBA, this, followed by that. And when we take the second strings of each pair, AB and BA, we also get ABBA. And this common string followed by the index string in reverse, which is that, will have two leftmost derivations, one starting with A and the other starting with B. Here is the derivation starting with A, and here's the derivation starting with B. So here's the proof this construction is a correct reduction from PCP to ambiguity. First, suppose the PCP instance has a solution, say represented by the sequence of index symbols A1 through AK. Note there can be repeats in this sequence. Then W1 through WK is the same string as X1 through XK. That's what it means for this index sequence to be a solution. Then there are two leftmost derivations of the string that is W1 through WK, or equivalently it's X1 through XK, that is followed by AK down to A1. One starts with S goes to A, and the other starts with S goes to B. For the converse, we're going to show that if there are two leftmost derivations of a string of terminals, then one must begin S goes to A, the other must begin S goes to B. Suppose there are two leftmost derivations that begin with S goes to A. Then we can look at the sequence of index symbols in the resulting terminal string in reverse and learn exactly the sequence of productions used. Except for the last production used, each would be the unique A production that generates the index symbol and has an A in the body. And the final production would be the one with the last, that is leftmost index symbol, and no A in the body. The same idea works for derivations that start with S goes to B. There can be only one with a given sequence of index symbols. Here's an example. If the derivation starts with S goes to A and produces a terminal string with index sequence 2, 3, 2, 1, then here's what the derivation of parse tree has to look like. Okay. First of all, we start with A. The first production used must generate the 1 at the right end, and we need to keep the A, so this is the only choice. So we've generated W1 off to the left of the A. The next index symbol from the right end is a 2, so we have to use this production. Again, we still need to keep that A there because we have more index symbols to go. Then the third from the left index symbol is 3, so this is the production we have to use. And then the last index symbol is 2, that is the leftmost index symbol is 2. So we're going to get rid of that A and use this production. That's the only way we could generate a string with 2, 3, 2, 1 at the end and no other index symbols. We can prove many things about context-free grammars to be undecidable as well, but to do so we need to show that the complement of a list language is also context-free. Remember that the complement of a context-free language need not be context-free, but fortunately these are. For the proof, we find it easy to construct a pushdown automaton, in fact a deterministic pushdown automaton, for the complement. The PDA we construct will start with a bottom marker on its stack. At first, some symbols from the PCP instance, not indexed symbols, will appear. The PDA simply pushes them onto the stack. After the first index symbol arrives, start checking that the proper strings appear on the stack. That is, if we see an index symbol AI, then check that the proper WI appears on the stack with the right end of WI at the top. The PDA pops all the symbols of WI if so. Note that we're assuming this is the complement of the list language based on the first components. If it is for the second components, we'll check that XI appears on the top of the stack, again with the right end at the top. What we seem to be doing is accepting the list language itself rather than the complement, but I didn't tell you when the PDA accepts. In fact, it accepts every input, with only the exception of when it has found a string in the list language. That is, if the input so far was some sequence of PCP symbols followed by some sequence of index symbols, and these sequences are not empty, and the bottom of stack marker is now exposed, then the PDA does not accept this string. It will accept any other string that follows, which cannot then also be a solution to the PCP instance. Now we can use the complement language. Let LA and LB be the list languages for the first and second components of an instance of PCP. And let LA complement and LB complement be their complements. Now all four of these languages are context-free languages. Let's consider the union of the complement languages. This is also a context-free language by the fact that context-free languages are closed under union. I claim that this union equals sigma star, where sigma is the alphabet consisting of all the symbols used by the languages involved, if and only if there is no solution to the PCP instance. Suppose there were a solution, say represented by the index symbols A1 through AN. Then this string is not in the complement of LA, and the equal string, this, is not in the complement of B. Thus, if there is a solution, there is a string missing from the union. Conversely, suppose string Y AN down to A1, let's say this, is missing from the union. That means Y is the string you get by using indexes A1 through AN and taking the first strings from the index pairs. And it's also the string you get by doing the same with the second pairs. That means A1 through AN is a solution to the PCP instance. We have now reduced PCP to the question, is a given context-free language equal to all strings over its terminal alphabet? Thus, this problem is undecidable. Here's another undecidable question about context-free languages. Is the language also a regular language? We do exactly the same reduction from PCP, and one direction is easy. If there's no solution, then we just showed that the union of the complement languages is sigma star, and that's surely a regular language. But we also need to show the converse, that if L, the union of the complement languages, is something other than sigma star, then it's not a regular language. Suppose we have a solution to the PCP instance, and in particular, let X be the index symbols in reverse. That gives you the solution, and let W be the string you get by using the first string from each of the indexed pairs in order, or obviously equivalently the second string from the same pairs. Now, let H be the homomorphism defined by H of 0 is W and H of 1 is X. Remember, L is the union of the complements, the strings that are not solutions to the given instance of PCP. We claim that 0 to the n, 1 to the n, is not an L for any n, because if we repeat a solution to a PCP instance any number of times, we also get solutions to that instance. However, H of y is an L for any other y. That is, H of y is not a solution. This point requires a little thought. First, If y isn't zeros followed by ones, then h of y isn't of the right form to be a solution to PCP. That is, it will not consist of PCP instance symbols followed by index symbols. But if y consists of n ones preceded by a different number of zeros, then it can't possibly represent a solution. H applied to the n ones gives a particular sequence of index symbols. But we know the PCP instance symbols that this sequence of index symbols corresponds to is H applied to n zeros. Therefore, it couldn't also be H applied to a different number of zeros. So if L, the union of complements, were regular, then H inverse of L would also be regular, because regular languages are closed under inverse homomorphism. And the complement of H inverse of L would be regular because regular languages are closed under complementation. But this language we just argued is the set of 0 to the n, 1 to the n, such that n is at least 1, a language we know very well not to be regular.